Hello, my mathematicians. Today we are starting with scale drawings. So we're pretty much done with scale copies, but now we're going to talk about scale drawings. So this is more like real life. So here are some drawings of a school bus, a quarter, and the subway lines around Boston. The first three drawings here are scale drawings of these actual objects because the bus isn't that small and a quarter isn't probably that small, okay? The next three drawings are not scale drawings of these objects. So let's talk about what a scale drawing is. So if we look at this, these are, does that show the original, the actual object accurately? Yes, it does. So a scale drawing shows the object accurately. Okay, and all parts in the drawing match the actual object, don't they? So the back of the school bus actually has lights, it has a door, it says school bus, it has four tires, an actual quarter has George Washington on it and looks like that. And then this is what the subway system around Boston looks like. So all of the details or parts in the drawing match the actual object. Now let's look at these non-examples, or why are these not scale drawings? Well, what's wrong with them? Well, this one is all squiggly and stuff, and this doesn't even look like George Washington. His nose is huge. And these are all straight lines, and they're not straight lines for the actual subway system. So we're going to say there are no distortions because these are distorted from the actual. Okay, and it's kind of like a scaled copy of a real object, but it's flat. So we could say it is a scaled copy, and we know what scaled copies are, of a real object, but it's 2D or flat. So it's kind of like a map, a globe. Those are scale drawings of the actual object. All right, so now we're going to start with this basketball court. And if you don't have a printer, you're not going to be able to print this out, and I understand that, but we are told that 1 centimeter represents 2 meters. So what I'm going to do is I'm going to first ask you, I'm going to tell you the measurements. So in this drawing right here, this is going to be 14 centimeters. When I measured it, the width was 7.5 centimeters. Hoop to hoop was 12.4 centimeters. And the 3-point line to the sideline was 0.5 centimeters. So I'm going to give you those measurements. Okay, so that takes care of part 1. Part 2 says, the statement on there says 1 centimeter represents 2 meters. That is the scale of the drawing. It can also be expressed as 1 centimeter to 2 meters, or 1 centimeter for every 2 meters. So what do you think the scale tells us? Well, is this kind of like a scale factor of 2? For every 1 centimeter, it's actually 2 meters in real life. So 1 centimeter on the drawing represents 2 meters on the court. All right, so now how could we figure out what the actual court is? Well, if the scale drawing is 14 centimeters and every centimeter represents 2 meters, I'm going to take that 14 and I'm going to multiply it by 2. So that's going to give me that this actual court is 28 meters. Now it's not centimeters, it's meters because 1 centimeter represents 2 meters. All right, so I'm going to do the same thing here. 7.5 centimeters. Every centimeter represents 2 meters, so that's going to give me 15 meters. Same thing here, 12.4 centimeters on the drawing. Each one represents 2 meters, so I'm going to multiply that by 2, so that's going to give me 24.8 meters in real life. And then 0.5, or 5/10 times 2, is going to give me 1 meter in real life, okay, on the actual court. So those are our measurements. Now, it says the bench area is typically 9 meters long. Is this in real life or is this on the drawing? Well, it tells us right here. This is in real life, the actual court. It's 9 meters long. Without measuring, determine how long the bench area should be on the scale drawing. Well, we'll go back up here. 1 centimeter represents 2 meters. Well, if we take 9 and we divide it by 2, because we're going to the scale drawing, which is the same thing as multiplying by the reciprocal. And remember, we learned that when you go from the drawing to the actual, or the original to the drawing, it's one way, and when you go back the other way, it's the reciprocal. So if we take this and we multiply that, we get 9/2, which equals 4.5 centimeters, because we're doing the drawing on the scale drawing. So the unit on the drawing is centimeters. So if we go in and we measure this, guess what? It is 4.5 centimeters. All right, so that's the end of activity 2. With activity 3, we're talking about some tall structures, and we're being asked to answer some questions, and you probably don't have a ruler at home. So we can go back to using that little piece of paper like we've done before about how tall is the actual Willis Tower. Well, we are told a scale over here that this distance equals 100 meters. So if I take my piece of paper here, I'm going to draw a tick mark here. So from here to here represents 100 meters in real life. So if I come over here to the tower and I just draw some tick marks, there's 1, that represents 100 meters. This is 200 meters, 300 meters, 400 meters, 500 meters, a little bit more than 500 meters. So we can say about 500 meters, or maybe 510, 520, somewhere around there, okay? How tall is the actual Great Pyramid? Well, we're using the same scale, so we're going to come over here. So this represents 100 meters, and then it looks like about half of that. So I would say that the Great Pyramid is about 150 meters, okay? About how much taller is the Burj Khalifa, probably didn't say that right, than the Eiffel Tower? Explain or show your reasoning, okay? So we're going to take, and I am going to draw a line across here where the Eiffel Tower is. Watch this. Okay, so that's where the Eiffel Tower is. And now I want to go figure out how much taller it is. So I'm going to use my same little scale factor. Let me find the right one. I've used this multiple times. Okay, there's my 100. So I'm going to go 100, 200, 300, 400, 500, plus a itty bitty bit more. We're going to call it about 500 meters taller. Because they're asking us to, I mean, it's not super accurate because we're using a little piece of paper. All right, so measure the line segment that shows the scale to the nearest tenth of a centimeter. Express the scale of the drawing using numbers and words. So when I measured this distance right here, I got 0.7 centimeters, and that represented how many meters in real life? 100 meters. So 0.7 centimeters on the drawing represents 100 meters of the actual height. That is our scale. All right. All right. So now for Are You Ready for More? The tallest mountain in the U.S. is Mount Denali in Alaska, and it is 6,190 meters. If this mountain were shown on the scale drawing, how would its height compare to the heights in the structures? Well, if we take that 6,190 and we divide it by 800, why did I divide it by 800? Oh, because this right here is 800 meters. This tallest thing is 800. So it is going to be approximately 7.5 times larger, taller than this tallest structure. Okay, so it's going to be a lot taller, because this is only about 800 meters tall and the mountain is 6,190 meters tall. All right, so scale drawings are two-dimensional representations of actual objects or places. Floor plans, maps are all real good examples of it. Every part corresponds to something in the actual object. Lengths on the drawing are enlarged or reduced by the same scale factor so we don't get any distortion. And we have to be given a scale that tells us how much of the actual measurement is represented on the drawing. Okay? Sometimes the scale is shown as a segment on the drawing itself, like this. Sometimes it's in words. Okay? Something you have to look for. All right, two definitions today. So, what is scale? Well, scale tells us, or tells you, how lengths in the drawing and actual, so the actual lengths correspond. An example would be 1 inch to 2 feet. That means 1 inch on the drawing represents 2 feet in real life. Okay, a scale drawing is where all lengths in the drawing correspond to lengths in the object by the same scale. They are not distorted. All right, hope you grew your math brain today and get those practice problems done. And remember, I'm here to help if you need help. Have a great day.